Welcome to the ABB session on asset utilization of data center topologies. I'm Harry Handlin, a data center solution architect for ABB responsible for providing technical and application support for ABB products in customer data centers. If this is the first session you were able to join today, a few platform basics will be useful. In addition to the slides, you will find resources available to you that include reference documents and links, as well as the survey you will need to send back in for CEU certification. A PhD certificate is also provided for those who prefer it. You'll notice an area to submit any questions that you may have throughout the presentation. As questions come in, we'll be collecting them and responding at the close of the presentation. Reliability is essential and expected in data center applications. Unfortunately, increases in reliability typically result in increased cost. This is because increases in reliability are the result of adding additional components or additional paths, which means more equipment and more cost. In order to reduce data center costs without sacrificing reliability, many data centers are increasing the focus on utilization. Increases in utilization decrease the cost per kW of a data center. As the data center market matures, we are seeing increased pressure to have data center operations contribute to the bottom line instead of having a negative impact on profitability. This has resulted in many data center customers focusing on utilization as a way to balance data center reliability with data center cost. Since reliability and cost are related, utilization is the balancing factor which can bring down overall cost without sacrificing reliability. We expect the focus on utilization to be a trend that will continue well into the future. Reliability and availability. Traditionally, IT managers have discussed applications in terms of availability. In other words, how often is the application available for a user? Usually it's measured in a percentage, like 99% availability. So it was a natural progression to apply availability to the data center infrastructure. While reliability and availability are similar, there are several significant differences. Reliability can be a better tool in assessing a data center design since reliability gives better granularity. Large increases in reliability as measured in probability of failure yield very small increases in availability. Therefore, it is easier to measure the cost-benefit and design changes using reliability rather than availability. Also, as shown on this slide, two systems with the same availability can have different reliability. Both systems have 4 hours of annual downtime. By definition, both systems have the same availability. However, System A experiences 1 outage during the year, while System B experiences 3 outages during the year. Therefore, the availability of System A is higher than the reliability of System B. Reliability of a critical power system can be calculated using IEEE P3006.8, the recommended practice for analyzing reliability data for equipment used in industrial and commercial power systems. This practice has not been widely adopted or accepted for data centers for several reasons. It is difficult to get accurate mean time between failure data for most of the electrical distribution equipment, like circuit breakers. The modeling is complex, and it's very expensive to have these kind of studies done to do the calculations. So we'll probably see a mix of reliability and availability used in assessing various data center designs. What is utilization? It is the ability to put to use of an item or a piece of equipment. Actually, it is the ratio of usage versus capacity measured as a percentage. The topology of the critical power system design has a direct impact on the utilization. An end system, which is a system with just enough capacity in the critical components like generators and UPS modules to handle the load, with no redundant paths or components, has a very high utilization but has low reliability. A system with redundant components, defined as an N+1 system, increases reliability and cost but lowers utilization. A 2N system, also called a system plus system, provides redundant paths which significantly increases reliability, but also increases cost and reduces utilization. With a 2N system, there are two independent paths which share load, so the maximum design utilization is 50%. A shared redundant system, typically shared redundant systems are 3N/2, 3 systems with 2 systems worth of load, or 4N/3, 4 systems with 3 systems worth of load, maintains the reliability while significantly increasing the utilization. For example, the 4N/3 design has a maximum design utilization of 75%. Isolated parallel ring bus systems, or IPRB, eliminates stranded assets, improves reliability, and provides high utilization. However, cost is still an issue with most IPRB designs. Block redundant or catcher systems achieve high levels of utilization with varying degrees of reliability. So we need to be careful at looking at catcher systems or block redundant systems. This is a basic critical power infrastructure, sometimes referred to as an end system. This design uses generators and UPSs sized to the load, resulting in utilizations approaching 100%. The drawbacks are several single points of failure and no concurrent maintainability. Single points of failure mean if the device or equipment fails, the critical load will be impacted. Single points of failure include the generator, the UPS, all 3 switchboards shown, and each of the PDUs. Typically, these systems use single-corded loads, resulting in the IT power supply also being a single point of failure. Concurrent maintainability means any piece of equipment can be taken out of service for maintenance without impacting the critical load. For an end system, concurrent maintainability is not available. Both of these deficiencies combine to increase the probability of failure, in other words, lower reliability. Lack of concurrent maintainability can also reduce system availability, since many maintenance activities will require shutdown of the critical load. A design with a single path and redundant components, referred to as an N+1 system, improves the reliability and the maintainability of the system by the use of redundant components, but there are still single points of failure. A single UPS module or single generator may be maintained without impacting the critical load, but many other components cannot be maintained without an outage. For example, the low voltage main switchboard, the UPS output switchboard, and the critical load switchboard cannot be taken out of service for maintenance without an outage. Therefore, concurrent maintainability of all equipment is not available for an N+1 system. Note the utilization of generators and UPS modules. In this example, both are supplied with N+1 redundancy, in other words, one more device than required to feed the load. However, there are 2 generators and 4 UPS modules. The maximum design utilization is 50% for generators and 75% for the UPS modules. System plus system offers high reliability with concurrent maintainability. It consists of two independent paths or systems, so sometimes it's referred to as a two-end system. Each system is designed to carry the full load. This system also uses dual-corded IT loads. This means each server, storage device, or network switch has two power supplies inside the device. Either power supply can provide the required power to the load. Typically, these power supplies share the load equally. The system plus system design eliminates single points of failure and also allows concurrent maintainability. The major drawback is the maximum design utilization is 50%, resulting in a very expensive system. So extremely reliable and extremely expensive. So let's take a deeper look at this system. This is a block diagram of a typical system plus system or two-end design. Note there are two systems, each with N capacity, meaning either system can supply the entire load. The system on the left and the system on the right are virtually independent. In this particular diagram, there is a connection between the two paralleling buses for maintenance, but in normal operation, the two systems would be independent. This diagram has redundant paths, but not redundant components in each path. So each system is redundant to the other. The system block diagram shown has two utility services, two generator paralleling buses, and two UPS systems. Each system normally supplies one side of the dual-corded IT loads, so that the loads are approximately equally split. Note there are no single points of failure. A failure of any component in the left system does not impede the ability of the right-hand system to supply power to the entire critical load. To ensure a failure on one system does not impact the other system, most designs physically separate each system. In other words, the two main switch gears would be in separate rooms. Therefore, if a fire or fault occurred in one switch gear, it would not impact the other switch gear and take both systems down. So very reliable system, very proven system. Concurrent maintainability is achieved because one system can supply the entire load while the other system's being maintained. For example, I could take out the UPS output gear on system B and therefore drop any possibility of system B supplying critical load, but system A could then assume all of the critical load for the system. Note the two-end system can support single-corded IT loads if these loads are fed from a static transfer switch or STS. In this case, the IT power supply and the STS become single points of failure. So typically dual-corded loads are recommended. So how can we maintain the reliability of a system plus system design, yet improve utilization such that we can lower overall cost? One way to do this is the shared redundant topology. Shared redundant is a similar concept to the system plus system design, but instead of equally sharing the load between two systems, it is equally shared between multiple systems. The most common shared redundant designs are the 3n/2 and the 4n/3. The 3n/2 uses three independent systems to feed two systems worth of load. For example, three systems with each having a capacity of 1,000 kW can feed a load of 2,000 kW, yielding a maximum design utilization of 66%. A 4 and over 3 system would have a maximum design utilization of 75%. So consider a 6 megawatt system plus system data center. Using the system plus system topology would require 4 systems of 3 megawatts each. Basically, 2 independent system plus system designs, each with 2 systems of 3 megawatts. So total capacity of 12 megawatts. Each system with 50% utilization, therefore I can get 6 megawatts of IT load. Now, using the same design except distributing the load across 4 systems would allow a 9 megawatt IT load. This represents a 50% increase in IT load for very little additional CapEx. Maximum design utilization 75%. However, there is a cost. Load distribution in a shared redundant system requires frequent monitoring of loads to ensure redundancy is maintained. This does have an impact on the OpEx or operational costs. The largest shared redundant system I have seen was a 9N over 8. This is a typical 4N over 3 shared redundant design. Like the system plus system topology, the shared redundant topology is concurrently maintainable and has no single points of failure. In this 4N over 3 example, the loads are connected such that with all systems operating, the loading on any UPS does not exceed 75% of capacity in order to maintain redundancy. With the system plus system design, there's a single load group, as all loads are connected between A and B systems. With the 4N over 3, there are 6 load groups. Loads are connected between System A and System B, System A and System C, System A, System D, System B and System C, System B and System D, and System C and System D. So with those 6 load groups, it becomes very critical to make sure that the IT loads are installed in the proper location to maintain the loading, to maintain redundancy. That's where the complexity comes in and why this requires more management and more attention to detail and increases your OpEx cost from a management standpoint. The block redundant or catcher design consists of normally active blocks or systems and a catcher or reserve block. In normal operation, the catcher or reserve block is not loaded. The active blocks are all the same size and can utilize either single or parallel UPS systems. The reserve block must be as large as the active block, or it can be larger, usually in multiples of the active block. Block redundant or catcher topologies utilize static transfer switches or STSs to create multiple paths. The STS is a sub-cycle transfer switch which can accomplish an in-phase transfer in about 4 milliseconds. Most current designs of STSs can also transfer in an out-of-phase condition. IT power supplies can ride through a 10 millisecond power outage. The block redundant design is based on the speed of the STS and the load step ability of the UPS. For example, when an STS transfers a load to the reserve block, the catcher UPS will see a step load. If the entire load block fails and the catcher is the same size as the active block, the UPS will see 100% step load. Block redundant can be implemented with single corded loads or with dual corded loads. With single corded loads, the STS becomes a single point of failure. This is a typical block redundant or catcher designed for single corded loads. In this case, the generators and the UPSs have a maximum design utilization of 75%. We have 3 active systems and 1 catcher system the same size as the actives. The STS and the PDU have a maximum design utilization of 100%. Note that in this case, the STS and PDUs are single points of failure, and the system is not concurrently maintainable because of the STS and PDUs being single points of failure. The design for dual-corded loads improves the reliability and adds costs. Typically, the number of STSs and PDUs doubles, but there are ways to reduce the number. One scheme to reduce the numbers and thereby reduce costs doubles the PDU count, but does not change the number of STSs. The most common implementation of block redundant or catcher are 4 active blocks with equally sized reserve block, or 8 active blocks with a reserve block twice the size of the active block. The 4-in-1 catcher or the 8-in-2 catcher both have a maximum design utilization of 80%. And now let's begin to address some of the questions that came in. Please feel free to continue submitting at this time, and we will respond to as many as we can.